So in this video we want to go through an example of changing the order of integration. So right here we have the integral from x squared to 4 and from 1 to 2 dy dx. So we're integrating first with respect to y and then with respect to x. And I have a picture over here of what this region of integration looks like, only because my hand drawing of it would be horrible. But you could draw the region of integration without having a graphic pre-done. And what we want to remember is that if we're integrating first with respect to y, then this lower bound of integration is going to be a y equals. So it's really a y equals x squared, and up here this is really a y equal to 4. So y equals 4 is just a horizontal line at 4, and y equals x squared, of course, is a parabola. And then you've got the x bounds, so this is really x equals 1 and x equals 2. So we're saying in this direction here, in the horizontal direction, go from 1 to 2. And so what we want is the graph of the parabola x squared over the interval from 1 to 2. So that's x squared, the y equals x squared, but constrained on that interval from x equals 1 to x equal to 2. And then y equal 4 is going to be constrained over that same x interval. The y function is going to run from 1 to 2, x equal 1 to 2 for the inputs. And here's the line x equals 1. And so what we want to recognize is inside the red outlined area, this region here is the region over which this integration is being done. So when we're integrating with respect to y first, we're running from our lower bound to our upper bound of integration. We're really running from the parabola up to, which is our lower bound of integration. We're running from that parabola up to the line y equal to 4 in this direction. And then when we integrate with respect to x, we're running over this x interval right here. So if we change the bounds of integration, if we change the order of integration and we want to do dx times dy first, the order of multiplication doesn't matter, but I will need to change the bounds of integration so that I integrate the correct region. And what I want to recognize is that if I do dx first, then I'm running horizontally parallel to the x-axis. So I'm running from this line to the parabola. So this line right here is the line I have to go with respect to x first, so it needs to be x equal to 1 is the left bound of integration. And I need to have a function up here, a function of y, because my next integration will be with respect to y. So this parabola, remember, he's just y equals x squared, but these need to be x equals for our bounds of integration with respect to dx. So I'm going to need to take the square root of both sides, and I don't need the negative square root because that would correspond to this part of the parabola. I need the positive square root, so I'm going to run from x equal 1 up to x equal the square root of y. And then you have to say, well, when I do that, what do the y values have to run from? Well, they're going to need to run from y equal 1 all the way up to y equal 4 to capture this entire region right here. So the dy's are going to run from 1 to 4. And then if we integrate both of these integrals, because we're calculating the area of the same region, we should get the same result regardless the order of integration, as long as we've adjusted the bounds of integration correctly. So like if we work this one through, this is really a 1 dy. If we integrate first with respect to y, we're just going to get y running from the lower bound to the upper bound, and I'll still have the dx because we haven't done that yet. 1 to 2, plug in the upper bound of integration minus the lower bound of integration dx. Integrate with respect to x, so we get 4x minus 1/3 x cubed. From 1 to 2, plug in our upper bound of integration, so we get 4 times 2 is 8, minus 1/3 times 2 cubed is going to be 8/3, minus plug in the lower bound of integration, 4 times 1 is 4, minus 1/3 times 1 cubed is just 1/3. And now just simplify. 8 minus the 8/3 minus 4 plus 1/3. 8 minus 4 is 4. Minus 8/3 plus 1/3 is going to give us a 7/3. And then a common denominator, that would be 12 over 3. And 12 minus 7 is going to give us a 5 over 3. If we integrate with respect to x first, we want to look at this and say, hey, that's a 1 dx. So when we integrate with respect to x, we're going to get just x running from the lower to the upper bound of integration dy. Plug in the upper bound and the lower bound of integration. So we're going to get the integral from 1 to 4 of the square root of y minus 1 dy. Or look at this as being y to the 1/2 power. Integrate with respect to y. So we're going to get, it's going to be y to the, we need to add 1 to that exponent. So it's going to be a 3/2 and a 3/2. And we'll need to kill that when we differentiate. So we'll have to multiply by a 2/3. And this will be minus, we integrate 1 with respect to y. We just get y. And we're running from 1 to 4. So we plug in our bounds of integration. We're going to get 2/3 times, we're plugging 4 in right here. So we have 4 to the 3/2 minus 4 minus parentheses 2/3 times 1 to the 3/2 is just 2/3 minus a 1. And then simplify. 3/2 for our exponent. So take the square root of 4 is 2 and 2 cubed is 8 times 2 is 16. We get 16/3 from there. Minus 4 minus 2/3 plus 1. So we have 16 minus 2 is going to be 14/3. Minus 4 plus 1 is a minus 3. So common denominator is going to make this a 9/3. And 14 minus 9 is 5 over 3. So we get the same result regardless the order in which we integrate, as long as we modify the bounds of integration appropriately.